Hello, everyone. Welcome to the July meetup of Women in Compilers and Tools. It is my pleasure to welcome Professor Alexa VanHattum as our guest speaker today. Alexa is an assistant professor of computer science at Wellesley College, at a historically women's college and liberal arts college. Her research sits at the intersection of programming languages and systems, with a focus on applying lightweight formal methods to the compiler stack. She recently defended her PhD thesis at Cornell University, where she was an NSF graduate research fellow, advised by Adrian Sampson in the Computer Architecture and Programming Abstractions group. She holds a bachelor's from Brown University and has previously worked on Rust verification at Amazon Web Services and health software at Apple. Welcome, Alexa.
Thank you so much, and thank you all for being here. So I'm really excited to talk to you today about my PhD research, and in particular, the last project of my PhD, which is this idea that we can use lightweight and modular verification to reason about instruction selection in a production compiler. So I'll talk about that, but then we also want this talk to be, like, by the end, kind of a career chat and an Ask Me Anything as well. So if you have any questions about my career trajectory or how the academic job market works, anything like that, you can save that to the end and we'll talk about that as well. So my clicker is not working. There we go. Yeah, so the work that I'll talk about today, the last paper of my PhD, which is currently in submission, is joint work with my collaborators, Monica, Chris, Adrian, and Fraser, across sort of industry at Fastly and a different institution, Carnegie Mellon. And what I think is pretty cool about this paper is it's actually the first project I've worked on in academia that is majority women. So that was a fun way to end my PhD. So just to give you an idea of kind of my journey, I know there are folks here from both academia and industry, and in general, compilers really sits across this intersection. And I just want to highlight my path kind of between the two. So I started off in academia. I got my bachelor's from Brown, like Juby mentioned, and I took this class at the end of my time at Brown called Logic for Hackers, where the idea was we can apply sort of formal logic in a very practical way to reason about systems. The class was called Hackers, which I didn't like. It's now called Logic for Systems. That was a better name, and I encouraged the professor to change the name. But that kind of got me interested in this world of programming languages, formal methods, compilers. But I took all of that excitement and basically decided I was just going to put it on hold because I really wanted to go and be a software engineer. So when I first left Brown, I went and got a job at Apple, where I worked on something totally unrelated to compilers. So I was a software engineer on the health team. I got to work on sort of general APIs and frameworks for health. So I got to think about how developers use software, but I was really just a software engineer, not particularly focused on compilers. But when I decided to go back into academia and apply for a PhD program, I knew that this intersection of programming languages and systems was where I really wanted to focus. So I applied and got into the Cornell Computer Science PhD program, went back to being a student, and then spent a while in academia there. And at first, it was a little bit hard to find my footing in academia. I sort of worked on really cool projects. I learned a lot about programming languages. I started having really great collaborators, but I wasn't really sure how to connect all of the sort of academic formalism to the real world. And what was really helpful for me in doing that was starting to kind of reach back to industry and collaborate with folks who are at companies and sort of working on more production projects. So the first paper of my PhD was a collaboration with folks at Facebook Reality Labs, as well as a few different other universities. So that was sort of the first project of my PhD, which I'm just going to really briefly highlight in this talk. And then I, in the middle of my PhD, decided to go and sort of fully embed myself in industry and do a PhD internship at AWS's automated reasoning groups. That's a group kind of dedicated to this idea of formal methods, programming languages, technique. How can we use that to build better software sort of in production and applied to the real world? And that formed the sort of middle project of my dissertation. And then finally, the actual focus of this talk, what I'll talk about for most of the next bit, was this collaboration with Bytecode Alliance, which is an open source alliance across a few different companies. In particular, I mostly worked with software engineers at Fastly. And together, those three projects made up my thesis, which is called Lightweight Formal Methods for Correct Efficient Systems Programming. And I just successfully defended this in May. So that was sort of what I found to be most fulfilling in my PhD, was trying to sort of straddle this line between academia and industry and keep sort of the formalism and the excitement of sort of next generation techniques from programming languages theory, but also apply it to real world problems and in particular systems programming in production systems. So then from all of that, I had to decide, what did I want to do next? And looking back at my path, what I realized is what I've always really liked is balancing teaching as well. So I taught a lot when I was at Brown, I taught at Cornell, and I decided that I wanted to find a position where I could teach as well as stay engaged with research. And so I accepted a position as an assistant professor at Wellesley College. And as mentioned, the kind of most important bits to know for the purpose of this talk about Wellesley College is it's a historically women's college, which I'm really excited about. And it has all undergraduate students. So there are no PhD students, and in computer science, no master's students. And what this means is it provides a really nice balance between research and teaching. So you still are given resources to focus on research, but you're also sort of part of your core job, and more of your time than maybe a standard professor somewhere like Cornell, more of your time is dedicated to teaching and having small classes with undergraduates, which I find to be really exciting. So that's sort of my path bouncing back and forth between academia and industry. And then I want to share how this has cohered into a thesis, and then I'll highlight the last particular project in my thesis. So overall, no surprise given that I'm giving this talk, what I like to think about a lot is compilers. So what a compiler does, as I'm sure most of us know, is it takes some code in a source language, maybe that's doing some iteration over loops, and it needs to translate that usually all the way to machine code and what we're thinking about. So while programmers get to think at a high level of abstraction, what actually is executing on the machine is much simpler and can do things like move numbers around, add particular numbers, compare numbers. It's working at a much lower level of abstraction. And when we think about what is the job of a compiler, what we tend to think about is efficiency. So we tend to want to know the compiler is doing a lot of this work of getting code to a place where it's actually runnable. And so once the code is runnable, how fast can we actually make it? Can we make it run much faster than you expect without a very complicated compiler? We might also be concerned with other aspects of performance like memory or energy usage. And all of these are really important concerns of the compiler, and why many people work on compilers. It's in pursuit of these two goals. But what I like to think about a lot as well is this idea of correctness, which is unsurprising. Compilers should be correct. It's really annoying if they are incorrect. And when we think about correctness, a sort of high-level intuition for how to put it is, does the generated executable actually match the programmer's intention? And most of the time, if you're a software engineer, not a compiler software engineer, you don't really have to think about this too much, because the general wisdom is that if you're running into a bug, it's probably not a compiler bug. And this is actually really sort of good general wisdom, because most of the compilers folks are using as sort of standard software engineers are super heavily battle tested. So if you're using a compiler like LLVM or GCC or many of these other very common compilers, they have thousands and thousands of engineer hours spent writing tests for them and just using them in the field. But there are a few reasons why I think compiler correctness sort of is a more important concern in certain domains. So the first reason is just that new compilers are everywhere. So we have an abundance of languages. Some of these languages are decades old, but some of them are 5 to 10 years old. And as we think about all of these different languages, we also have an increasing number of targets. So oftentimes software is being run on a computer, but when I was working at Apple, I was mostly writing software for watches and iPhones, which are sort of different devices. People, are writing software for the cloud and this general idea. I could add here, light bulbs and refrigerators. Software is being run on more and more targets. And the truth is that when you have some new language, or if you have a new hardware target that isn't using an existing architecture for the low-level instructions, then you fundamentally need a new compiler to translate to or from respectively. And it's going to be the case that this new compiler is just much more likely to have correctness bugs. It's not as heavily tested, and so it's going to be more likely to have issues that could impact the correctness of the final program. Another context that I like to think about, and that's particularly relevant to this talk, is that sometimes compilers need to handle code that you fundamentally don't trust. And this is different from the original way that, when computing was developed in the past, 50 years. Initially, computers were at universities, and the code that was being run was, an employee of the university, or more generally, if you think about sort of the initial context of computing, it was okay if the compiler had a bug because it would probably just crash your code, and maybe that was okay. But additionally, or increasingly, we have these languages like JavaScript and WebAssembly that are meant to be run in the browser, where you might actually, by clicking on a link to some website, be downloading code that someone else wrote. And then if you think about the person who wrote that code, they might not necessarily have your best interest at heart. So there could be malicious actors trying to write code that targets the compilers that run in the browser or in a server client context to exploit your data. So maybe to steal your passwords or something like that. And in this sense, even a bug that is extremely rare and requires a really, really convoluted program to trigger a compiler bug, that's still a problem because that bug can be intentionally targeted by malicious actors in order to sort of exploit what should be security guarantees. So for that reason, correctness is more forefront in my mind sometimes when I think about research, as well as efficiency. And a sort of fundamental truth in lots of computer science, but in particular in compilers, is that these two goals of efficiency and correctness actually sort of have an implicit trade-off between them. And usually this trade-off isn't really direct. You're not trying to say, hey, I have a compiler, it's super, super efficient, but it's really buggy, please use it, right? No one wants their compiler to cause all sorts of security bugs. So instead, the way this actually occurs is that compiler engineers have sort of a finite amount of time, and they have to focus on, am I going to add new optimizations and make the code more efficient? Or am I going to sort of validate the code I already have for correctness? So fundamentally, there is a trade-off here. And if we think of this trade-off along this sort of graph, you can picture what I'm saying as a trade-off sort of in units of effort as this curved line, where for the same amount of effort, you can have a really efficient compiler, especially a new compiler that maybe isn't focused on correctness, or you can spend a lot of time focusing on correctness and maybe put less time into efficiency. So a compiler like LLVM has, thousands of engineers of compiler effort in it. And so it's really pretty good on both of these fronts. It's a very efficient compiler, and it's very, very correct. It's sort of rare for a working programmer to hit an LLVM correctness bug, but it's still not perfectly correct. There are still, new LLVM bugs found every week or every few weeks. But if you're trying to create some new compiler, then it's going to be at a completely different point on this chart. So say you have less than one engineer year of effort, your compiler is probably not going to be very efficient because there's a huge laundry list of optimizations you might want to implement for it to be efficient. And it's also probably not going to be very correct. And so the overall goal of my research is to use these techniques in the toolkits of formal methods to push upward on this curve without expending more programmer effort. So the idea is to sort of have the applied logic inherent in formal methods do the work to make your code more efficient or more correct along this curve. And I want to be clear, this is not sort of my invention. My particular focus is just applying formal methods in this context where efficiency is particularly important. So my PhD thesis, if I were to summarize it in a sort of high-level sentence, is that compiler stacks can use lightweight formal methods to produce correct and efficient systems code. And what I mean by systems code is, code that's focused on the low-level interfaces, oftentimes with hardware. So code that's used to interface with the operating system or with hypervisors, code that's used sort of to interact with the low-level components of computing. And I'm just going to really quickly summarize the three projects again and position them again in collaboration with industry. So the first project I worked on was vectorization strategies for energy efficient hardware, in particular, these funky pieces of hardware called digital signal processors. And this was a collaboration with Facebook Reality Labs. I then, in my internship with AWS, worked on a verifier for Rust called Connie. So in this particular system, it kind of inverts the relationship between formal methods and compilers, where Connie was not verifying a compiler, it was a verifier for Rust. But to make Connie work better, my contribution was to use compiler internals to actually speed up the verification. So there's this nice interplay between formal methods and compiler structure. And then finally, the paper that I'll talk more about today, or the project I'll talk more about today, is called VeriISLE, which is verifying instruction selection rules within a compiler from WebAssembly to native code. And this is a collaboration with the Bytecode Alliance, and in particular with engineers at Fastly. And what I think is really exciting about all of these projects and the strategy in general is that if you kind of look at the arrows here, which are meant to indicate sort of the direction the research is pushing in. So in some cases, we're pushing code to be more correct, and in some cases, we're pushing code to be more efficient. But no matter what, with all of these projects, if we're pushing in the direction of correctness, and especially correct by construction optimizations, this also lets us innovate faster. So when you know that you have a way of checking whether your optimizations are correct, you can be more aggressive with the type of optimizations you try to implement and therefore end up with faster code. So I really briefly want to just highlight what I mean here by lightweight formal methods as opposed to maybe formal methods in general. So I'm going to quickly go over related work. or just kind of what exists in the domain of formal methods for compilers for systems programming. So first of all, software engineers oftentimes first sort of tool to use if they want to check the correctness of their system is testing. Where the idea of testing is you have a bunch of different source code programs, you input them into your compiler, which you kind of envision as a black box, and you get out some machine code. And you oftentimes are checking really simple properties, like maybe just does it not crash? In some cases, for particular source code, you might have an idea of exactly the code it produces and do sort of file level tests. The problem with testing and why it's pretty far left here on the spectrum of correctness is you're only testing specific pieces of source code. And within those specific pieces of source code, you're probably only testing specific inputs. So if you have a function that, reads a single number and then does something with it, you're only testing that one program, and you're also potentially only testing one particular number. So there's a lot of spaces where your compiler could still be wrong, but you aren't catching. Okay. Can folks still hear me? Am I back? I think I froze for a second.
Yep.
Okay, great. Sorry about that. All right, so on the other end of the spectrum, so much higher level, kind of the highest level of state-of-the-art assurance of correctness is to use what I'm going to call foundational formal methods, oftentimes interactive theorem proving, to have a kind of clean slate design where from the ground up, you verify every piece or almost every piece of the compiler, oftentimes by exploiting this relationship between programs and proofs, where you're sort of building programs that have exactly the specification for what you want to do them. One of the really foundational pieces of work in this lineage is called ComCert, which is a formally verified compiler for C, verified almost the entire thing. In some cases in the original version, parts of the linker weren't verified, but now almost the entire pipeline from C to assembly is verified within ComCert. And there are other related projects for subsets of LLVM and for ML-based languages. And what's great about foundational formal methods is here, what you're inputting into your compiler is not individual source programs, but instead you're getting this guarantee over for all possible source code. Oftentimes you do this by composing the compiler into a bunch of individual passes that you prove individually, and then you get out some machine code. So the good things about this is that you get guarantees for all input programs and all inputs to this program. So I'll actually, in this example, where we have a number going in, you get the guarantee over all numbers. And you also have a, and the downside here is that when you actually think about the input language, it's typically a sublanguage. So ComCert restricts itself to a subset of C, and many of these other programs have to kind of not handle the full breadth of languages, and instead are working on oftentimes very usable, but smaller subsets of the language. And they also, the sort of biggest downside to this approach, or the biggest challenge in this approach, is that it requires just massive amounts of manual proof engineering effort. So ComCert took sort of engineer years, and not just engineer years, but expert proof engineer years in order to implement a C compiler. And this also means that ComCert does not have anywhere near the number of optimizations that systems like LLVM have. So where I like to position my research is in this separate regime, kind of in the middle, that I like to call lightweight formal methods, where you are able to get a higher assurance of correctness than testing, but not necessarily go all the way to foundational verification. And this lets us say useful things about programs, and in particular, find bugs in compilers and in systems code without needing to spend as much programmer effort. So some existing systems here include this idea of translation validation. So one of the coolest systems in this domain is called Alive2 for LLVM. And one of my earlier projects, Diospiros, does translation validation for a subset of C in our domain-specific language. And the idea with translation validation is that you still have sort of individual source code that you are running through the compiler. But instead of just getting the machine code out, you actually, for each particular input, are saying some sort of proof between the source code and the machine code that comes out on the other end. So this is great because if you know your program ahead of time and you're willing to pay the costs at compile time, you can actually get a similar guarantee. The problem is this has to sort of execute as you get source code, and oftentimes this doesn't scale to really large programs. This is true with all of these techniques, that sometimes formal verification is difficult to make scale to large programs. Another sort of regime of work or thread of work that I like to put in this lightweight formal methods category is to verify individual components of compilers. So to consider large parts of the compiler to be trusted, meaning you aren't looking for bugs there, but instead focusing your verification on a particular compiler area. So examples of this are people optimizations or people optimizers. So again, this project Alive, an actual earlier version of Alive, was focused on verifying people optimizations. What that means is it's just you have a window of instructions in the compiler's representation or the intermediate representation of the compiler, and you want to rewrite those to a different set of instructions in the same language that have a more efficient implementation or more efficient characteristics. There's also lots of verified components for JITs or just-in-time compilers. Examples of this are Vera, which was a system for verifying the range analysis. So basically in JavaScript, to get JavaScript to run fast in the browser, if you want to actually be able to reason about numbers, you want to have an idea of the range those numbers can take. And then Jitterbug, which was an implementation of looking at BPF, I always get that one wrong, in JIT. So this is basically looking at part of a language to extend the Linux kernel and trying to verify seed code in that domain. The particular project that I'll talk about for the remainder of this talk is called VeriISLE, and the part of the compiler that we're interested in is instruction lowering or instruction selection. So the overall idea of this verified component thing is that you still want to have a for all over all possible input programs, but the part of the compiler that you look at is just going to be one piece of the compiler. So you're looking at a specific pass or a specific analysis, and you still have this guarantee over for all inputs, but one particular component. And this, in practice, has been shown to find really critical bugs. So what I think is cool about this is that this can sort of be integrated into production compiler systems without having to sort of fully hitch yourself to the formal methods wagon from start to finish. You can just verify an individual piece of the compiler that you're worried about. So again, this project, we're back in this context where the code that you're running is code you don't necessarily trust. So in particular, this project looks at a compiler from WebAssembly, which is a bytecode language that is used, it's meant to be a portable format for the web. So it was originally designed to run code more efficiently and portably on the web, but it's also being used in different domains. So this is one of these examples where we might want to use WebAssembly outside of the browser alone. So Cranelift is a compiler that translates from WebAssembly to native code. And because WebAssembly as a language provides really nice security guarantees, it has sort of grown in usages outside of just the browser. So in particular, WebAssembly has this really nice idea of software-enforced isolation, where the language itself requires that code and data be separated, they can't access each other, and that individual instances of WebAssembly programs or modules must sort of only read their own data. And this is, of course, meant to say that when you run WebAssembly code in the browser, you don't want someone else's WebAssembly code to be able to go and read passwords that are stored elsewhere in your browser, for example. But folks at companies, including a lot of the companies that make up this Bytecode Alliance, have realized that you can use this for other things as well. So they want to do things like run clients' code on servers located geo-distributed all over the world. And there's this problem that when you're sort of doing this like function as a service style thing where you want some customer or client to give you a piece of code and you want to run it really fast, if it's a really short piece of code and you run this via sort of more traditional cloud computing mechanisms, there's a cold start time. It takes kind of a long time to run this new instance of code. But via a language like WebAssembly, you can try to enforce sort of separation between your different instances at the software layer instead of using traditional OS mechanisms. So in particular, this runtime for WebAssembly called WASMtime is trying to run multiple WebAssembly instances within the same operating system process. And this allows you to avoid the cost of starting up a new process or a new thread as you get sort of functions to run from your clients. But what this means is that the compiler's correctness is really, really important. If there's a bug in the compiler, a malicious client could send you a module that exploits that bug in order to read a different instance's memory. And unfortunately, that is not just like a theoretical concern. There have actually been bugs that folks have found that could cause this sort of exploit. So Cranelift has had a bug in instruction lowering in particular that had this characteristic. So this is a bug that was not found by our tool or found by me, it was found by an engineer, Alex Creighton. But the overall headline of the bug, this is the GitHub report, is that a guest could have a guest-controlled out-of-bounds read or write on the x86 backend. So in particular, this bug is a 9.9 out of 10 severity, so very, very severe. And the code generator Cranelift had a bug where an individual instance could access virtual memory 6 GB away from the base of linear memory, meaning from the sandbox that it was supposed to be constrained to. So this just goes to show that this idea that compiler bugs can be exploited is not just something we think could happen, but there have been actual instances where really critical bugs have been found in these parts of the compiler. So to explain this a little bit more, I'm just going to briefly again sketch the structure of lots of compilers and Cranelift in particular. So you have some source code, which in this case is WebAssembly is the sort of input source code to Cranelift. And then you have some sort of parsing or translation of that source code. And then a lot of what actually happens in the compiler, including some shared optimizations, is done on Cranelift's intermediate representation, or IR. And then the step to go from that intermediate representation to a machine code model is called instruction selection. So this is where we go from operators in the IR to specific operators that are on the particular target. So maybe you have an x86 target, or maybe you have an ARM64 target, and you would have different implementations of instruction selection for those two instruction set architectures, or ISAs. So usually when compilers are trying to do instruction lowering, they do this with ad hoc compiler code that looks for patterns in the instruction set, or in the IR representation. So this is a screenshot from an older version of Cranelift, where what you see is sort of Rust code using ifs to check for whether some particular value in the IR node is negated, and if so, choose one version, and if not, choose a different version. And the Cranelift engineers had a really great approach that they started taking around a year and a half ago, maybe 2 years now, which is that instead of having this ad hoc compiler code, they really wanted their code to be easier to understand, to be more declarative, and to be more amenable to verification. And so they rewrote their instruction selection to instead use a custom domain-specific language, or DSL, to rewrite code. So here you have some code written in this language, or this DSL called ISLE, where you have individual rules where the left-hand side, which here is listed first, let me show that, this I'm calling the left-hand side, has terms in Cranelift's IR and then some inputs, and the right-hand side has terms in the machine code, or the ISA, and the rewrite rule is going to replace the ad hoc compiler code. So for example, if we wanted to implement the most efficient machine code for an integer add, which Cranelift calls an IAdd, we would do this with multiple rules, each of which defines a partial function, meaning it only matches on some input potentially, and other rules will match on other inputs. So here's a particular rule where we are checking that some IAdd, which you see here in green, that has 2 arguments, x, and a second argument that is some other term, can be lowered to, or sort of select the machine instruction add with immediate. So what this is looking for is it's taking advantage of the fact that lots of backends have ways where if one of your arguments to an arithmetic function is a constant, you can actually store that constant in the instruction itself to avoid using an additional register. But what makes this rule really challenging, if we think about, how do we know that this rule is correct? In part, we have lots of different semantics running around here. So in green, we have a Cranelift IR term, and in red, we have an ARM machine code term. But then in addition, we have all of these other terms that I kind of glossed over. We have lower, has type, fits in 64, M12 from value, that are all constructs in ISLE that are helper terms to call out to external Rust code. So this is what makes ISLE a lot more expressive than some other DSLs, like the original version of Alive that was used for rewriting people optimizations. So what ISLE can do is engineers, without touching the core ISLE compiler, can define their own operators that are implemented in external Rust code. So you can define sort of arbitrary predicates that call out to a separate implementation in Rust. So when we think about how are these rules correct, we needed a way of saying how all of these different semantics interact. So example, if we look at this challenge of ISLE terms calling Rust code, if we looked at that it's in 16 term, that actually calls out to this implementation that checks whether the bits in the type are greater than or less than 16 in this case. So our approach is that engineers add inline annotations. So we introduce a new annotation language that allows users to sort of add engineers to, as they're adding new ISLE predicates and terms, can also provide spec annotations in a similar language to ISLE itself. So here you can say that fits in 16 can be summarized by it's actually going to return the type. It takes a type and returns a type, but it's a partial function. And we'll specify that with this require block that says that the function is only defined if the argument is less than or equal to 16. So our annotation language is essentially SMTlib. If you're not familiar with this, this is a sort of interface to a solver that is going to return whether or not logical formulas are satisfiable. Provide blocks specify the semantics of the return value, and require blocks specify when the match is defined. So the overall structure of the system, this is going to be my only slide that has actual math on it, so please bear with me a little bit, is that we have ISLE rules that were written by Cranelift engineers, not by the research team. And then we have term annotations, which are mostly written by the research team, but in collaboration with engineers. So these feed into our system. And what our system takes is shown here on the right. So we have some inputs. So these are sort of not known. They're symbolic values that are sort of bound variables in the rules. We have the actual term values. So what term arguments and returns are. We have the provide blocks and the require blocks. And then we have the outermost return that she'll call ret. And we have this translation function that truncates to match a given width. So our system works by first checking for a given rule, should the rule actually trigger? So rules are partial, and we need to actually check whether the rule will apply. So we call this the applicability check. And we ask whether there exists some concrete inputs and some terms such that the provide blocks, which provide the semantics of both the left-hand side and right-hand side block, are true, and whether the require blocks, which you can think of as sort of preconditions for when the rule should match, of the left-hand side are true. So if this query succeeds, so we feed this to the solver, we get back a result. If this query succeeds, we then want to ask the question, is the rule correct? So does the value produced by the machine code on the right-hand side match the value we expect by looking at the intermediate representation on the left-hand side? So the correctness query now becomes, instead of the there exists, which is that backwards E, we now have a for all. So we're saying for all possible inputs and terms, is it true that the preconditions on both the left and right-hand side, or sorry, the provides, which are the semantics on both left-hand side, and the require, which is like a preconditions, should all imply that the two return values are equal with this operator, that one of the return values needs to be truncated to capture the lower bits. And also we want to show that the require blocks on the right-hand side are true. So that's a lot of math, but the overall intuition is basically we're saying when you have a rule, consider the variables of the rule to be any possible input and ask if you can find a counterexample of those variables such that the machine code that you produce has a different answer. So what we get out from the SMT solver is either one of these counterexamples or verified equivalence that this rule is correct for all possible inputs. So going back to the bug that we saw initially, so again, we did not find this bug, but we are able to reproduce it. So I'm going to walk you through this bug. So the bug was in this rule, which is handling addressing mode on the x86 backend. So the only thing you really need to know here is that this is basically looking for cases where you're computing an address. So if you look here on the right-hand side, you're computing an address that has the form where you have some offset and some base that you're adding together. And then you're adding an additional integer that is shifted left by some concrete value, 1, 2, or 3. So we're in particular looking for small shifts, and then extended to 64 bits. So this kind of conceptual part here matches this here in the Cranelift IR, an extend that has an argument which is a shift, which has an argument which is some variable x, and some constant shift amount shift. And then we have a predicate that shift should be less than or equal to 3. And then this rule rewrites this to a single addressing mode on x86 that has a extend of a 0 extend. So that's the same thing as this unsigned extend here, taking x and taking the shift. So it seems like this should be the same instruction. But when we run this through our verification, we get this result that we have a different left-hand side and right-hand side, and it gives us the concrete inputs in blue that produce a different left-hand side and right-hand side. And in particular, you'll see that these numbers are almost the same except this 3 here. What's really problematic about this is that these are addresses which are supposed to be 32-bit addresses. So the fact that this 3 is existing, this is a number shown in hex, at a sort of higher bit than should be possible is really problematic. And this is what's allowing this instance, once we use this addressing mode to access memory on the hardware, which is a 64-bit machine, this is going to allow us to access memory totally outside of the instance we're looking at. So conceptually, what's happening here is on the left-hand side, we have a 32-bit value. We're shifting it by some amount. And when a 32-bit value is shifted by some amount, you sort of lose the high bits. You just drop them off the face of the earth. They should be gone. And then you extend that value to 64 bits, and this is the output. The problem is that the right-hand side does this in a slightly different order, where it's a single instruction that has a 32-bit value, it shifts, and then it extends. So this allows the left-hand side and the right-hand side to be distinct in a way that allows the right-hand side to produce a sandbox escape. So this is bad. And our tool can reproduce this in a matter of seconds. So overall, this tool reproduced 3 known historical correctness bugs. We also identified 2 new bugs and a new root cause, which I don't have time to go into. And we verified all integer operations. This is excluding loads and stores, but all sort of arithmetic integer operations for WebAssembly 1.0. And the key contribution and sort of what you can take away is that by using a declarative domain-specific language and these modular annotations, we can have production compilers that can benefit from formal methods even before they have a full formal semantics. So Cranelift IR does not have a full formal semantics, but we're still able to benefit from the contributions of formal methods. I have some ongoing and future work in this specific project, including integrating our verifier into mainline Cranelift with CI. So we're actually using GitHub Actions CI to run this in our own fork, but we want to integrate that back into mainline. We want to explicitly support these side effectual operations like loads and stores. And we want to expand coverage for new features in WebAssembly 2.0, including I-128 and SIMD instructions. So overall, my sort of vision and my goal is to enable lightweight and modular formal methods for efficient and reliable systems code. So yeah, I've worked with C and C++, with Rust, with WebAssembly. I'm excited at working with new languages, and I'm excited about working with all of these different backends. So finally, thank you for listening, and feel free to ask me anything. We can maybe start with technical questions about the talk, but then we also have time to go into lots of other questions as well. Thank you.
Thank you so much, Alexa. This was really a great talk, and it was refreshing for me to, kind of go over the topics that I was also kind of studying in both Cranelift and otherwise. So thank you. And there were great findings, especially the bug that you showed. That was pretty cool. So I would like to open up the forum to the audience. If you have any questions, please feel free to, post it on the chat, or you can turn on your camera or mic, whichever way you feel comfortable with, to ask any questions. To make it a comforting start for the audience, in case they're waiting for someone to get started. I have a question. So I wondered, like when you were showing that one particular slide in which you captured, how your projects kind of, started to move along that curve of efficiency versus correctness. I think, that was, very solid slide for me in order to, just see like, where every project was fitting in. But I wondered, like when we are in the PhD program, early years of our grad life and so on, like how was it for you to kind of, pinpoint, those projects and pick those problems, because it gets very stressful to, even understand what the right problems are, and, should I be solving X versus Y? How should I narrow down my scope and so on? And to the journey of connecting those dots together and bringing it all together to one picture. So would you like to share something about that?
Yeah, that's a really great question. And I think I kind of maybe hinted at this, but for me, what I think was really motivating is that I had to sort of start from the premise that knowing myself, I'm someone who really likes to collaborate. And so early on in my PhD, I was working on a project mostly just with my advisor, with a sort of bigger group, but my piece was really just me and my advisor. And I found that much more difficult to know if I was going in the right direction and to stay motivated. And so I sort of picked projects in part by thinking about who I could work with on them, which might sound a little silly. Maybe I should be motivated more by some like pure intrinsic goal for what exactly I wanted to do. But I think it's fair when you start a PhD that you don't know exactly what you want to study, and sort of learning from the smart people around you is a great way to start. Mm-hmm. And then I think for me, what also helped is this question of like, if in 5 years, the collective research agenda of like formal methods and compilers works, what are some things I want to be true? And for me, I really want it to be true that formal methods are more accessible for engineers who don't have PhDs. And so I tried to also sort of pick projects in that direction. And I think it was sometimes hard because what my advisor, the initial projects that my advisor had maybe were different than what I had originally, or it sort of can be hard to find the right balance of working with your advisor, working with other folks. And I think it's just good to try different things. Like the internship I did in the middle of my PhD was pretty different from the prior research I had done. And I found that very motivating as well to learn about a different area. Does that answer your question?
Yeah, of course. And I think you also brought up a very, important point, which I had on my mind to even follow up on, the collaborations. So as a student, it is also harder to figure out with whom do we want to collaborate. Like, what really helped you get out of your own lab? Was it like the, other labs in Cornell, or was it like, did you have any network prior to joining PhD? How did you find out, like, with whom do you want to actually, start working on different problems?
Yeah, that's a great question as well. So I did not have much of a network, especially in research before I started my PhD, mostly just sort of my undergrad advisor. And so the way I was able to bootstrap external collaborations is actually that I started working with a lab mate who had interned in a particular group. And so the members of that industrial group started sort of hanging around our Slack or whatever. And I was able to use that as a jumping off point to start that collaboration with, that was with Facebook Reality Labs, or Meta Reality Labs now. And from that, we are also able to pull in one of my advisors' grad school collaborators. So that's another place, is to kind of go to your advisor and figure out, of folks they've collaborated with in the past who are now at different institutions and maybe have different PhD students, are those folks that you might be interested in collaborations with. And then parts of my collaborations grew out of my PhD internship at AWS, that I was able to sort of leverage my first collaborator, who was a applied scientist at AWS at the time. I applied with the general bucket, but it always can be helpful if you know someone in a particular group as well. And then finally, this final project was much more of just figuring out the project I was interested in. I became really interested in Cranelift, and Cranelift does a really awesome job of making their open source project not just a name in that it's open source, but they really make it very open to the community. So they have open meetings that you can sign up for just on their GitHub. So I started attending those meetings, started sort of forming relationships with engineers, asking questions. And then I was able to pull in researchers at a different university through a totally ad hoc mechanism where sometimes you just meet folks either when you're visiting their school or they're visiting your school. And so I was able to meet collaborators just via university visits and turn that into a collaboration as well. Yeah. I think going to conferences can be really great for this as well. I know conference funding is hard. In compilers and programming languages, there's the Programming Languages Mentorship Workshop, PLMW, which can be a really great resource for early students to get a funded trip to one of the 4 major PL conferences. For computer architecture, there's also a program called YArch that does the same thing for some of the architecture conferences. So using that as a way to go to conferences, and not just trying to form collaborations with maybe very established professors, but also with other students who are your peers who might also be working on really cool things.
Yeah.
I see there's a question in the chat, so I might jump to that next. So the question is about what challenges do I foresee in verifying instructions like load and stores that are effectful? That's a great question. So one of the major challenges is just that solvers have a much harder time with reasoning about things that operate like functions instead of things that operate like values. So the nice thing about VeriISLE so far is that when you just have things that can be modeled as sort of pure functional values, solvers tend to respond in seconds. So the 97 rules that we verified, all of those 97 rules, or maybe all but 10, almost all of them terminate within a couple minutes, and 5 minutes total for the whole suite. There are maybe 10 rules that take much longer because they use operations like divide and multiply that solvers also have a harder time reasoning about. But when you think about operations like load and store, what a load and store is really is you have some sort of theoretical idea of memory. You ask for memory at a particular address, and the way it should operate is like a function in that, once you've stored a value, you should be able to load it and have it be the same value. So even if you're trying to have a very simple memory model, you need to have this idea of either having an array-like structure or a function-like structure. And we've just found that the sort of best SMT encoding of this, that's the most logical or most intuitive, is really, really slow when you get to bit vectors that are 64 bits wide. So that's one challenge, is just figuring out what is the right way to encode this into SMT such that it performs efficiently. And the problem, what kind of makes this harder in some ways than things like Alive2 that reason about LLVM, is that we really care about the exact addresses, because we really want the exact addresses to fall in a particular bucket. And I haven't worked on Alive2 specifically, and actually Juby, I think maybe has, so maybe you can correct this better than me, but one of the tricks that they describe in their paper is that they sort of like bucket addresses or simplify addresses into a smaller domain and then reason over that smaller domain, because you're just kind of reasoning about generic pointers and not the specific addresses. So that's sort of one challenge that becomes more difficult. And we also are just still figuring out, in collaboration with the Cranelift engineers, what exactly is the machine state that we should model. So for this particular version of instruction selection, this happens before register allocation. So sometimes when you're thinking about machine level code, you have the exact registers that are being fed in, and you can really just model like changes to the register file. We don't have that. At this point, registers are still abstract. So we need some abstraction for thinking about machine state that isn't quite all the way at the lowest level of assembly, but still captures what we need to reason about the correctness of instruction selection. And then another question in the chat is about my AWS research internship experience. Could I share how I prepared for the interview? Yes. I think they did not ask me like a programming question per se, but that same season I was applying to like other internships and I did get asked a programming question. So I think it was helpful that because I had been a software engineer, I had been an interviewer in programming, like software engineering, leak code type questions. So I think the standard advice is, yeah, even if it's been a while since you've done one of those, like go and practice like reversing the linked list, doing like the basics of programming if you think you might get like that level of technical question, depending on the internship. Other than that, what I did was I knew the general sort of team I was talking to. So I went and looked at their open source projects, read sort of experience reports that had come out of that particular team. I think that's really helpful so you can express interest in what they're doing in particular. And I also just did like the standard kind of interview questions, but applied to research. So questions like, what was a time when you had a research challenge that you weren't sure how to approach it? Or what project you've done so far are you most proud of? So some of these kind of questions reflecting on your past work, even if you don't have publications. I think at the time I had a publication, maybe it was even just a workshop publication. I don't quite remember the timing, but I think focusing on how to describe your own research and how to situate it in regards to what that particular team works with can be really helpful for PhD or research internship interviews.
Thank you for sharing that. I think it will help a lot of students who are looking for internships in general. And I think, yeah, it would be nice to kind of learn a little bit more about what you are trying to get next in your future research. Are you in tie-ups with the Cranelift team again, or are you also working with different compilers in different industries or some other labs?
Yeah. In the sort of immediate term, I am still very much collaborating with Cranelift. I'm really excited to try to move this code into actually being production usable. And I think we're going to run into some problems around sort of HCI and how do you make the sorts of errors that you get out of a formal methods tool appealing to the widest range of developers. So there are a couple of sort of core developers of Cranelift who are already really excited to use the tool, but Cranelift also welcomes contributions from lots of people who don't work at any of these companies. So how do we make it accessible for those folks to use verification as well? Sort of more broadly, I'm really interested in sort of Rust as a language, and I've worked on some other projects with verifying Rust and with trying to understand how the language level guarantees of systems like Rust can be threaded through the compiler. So I think there are cases where when Rust goes sort of all the way to LLVM, we lose some analysis, and how can we thread that through? That's a direction I'm interested in the future, although I don't have any like ongoing collaborations. And I think in general, this general pattern of expressing things as rewrites, and in particular, using a technique that I didn't have a chance to talk about today, but I used earlier in my PhD called equality saturation. We actually reason about many rewrites happening at the same time is a direction I'm excited in. There's a workshop called eGraphs that I've reviewed for that I think is a really great community. So I think continuing to do research in that direction is also exciting to me.
Yeah, absolutely. I think we can switch the gears a little bit towards academic job search.
Yeah, there's one question in the chat that is sort of about that. What was challenging about transitioning back to academia after industry? That's a great question. I think the hardest thing for me was going from feeling very integrated in a team and very like having constant feedback and very frequent feedback and concrete goals happening very frequently. As a software engineer, you might have daily stand-up, you have like week level goals, term level goals, you have all of this structure. And when you go back to academia, all of that is gone. You might be in classes, which provide some structure, but the important part is your research, and your research tends to have very little structure. And so that was the biggest challenge for me, the lack of structure and it being a little bit harder to like work with other people as frequently, I think were the two hardest things. There's also, there is a pay cut that can be a little bit difficult. I will say that working in industry first as a gap in between undergrad and PhD makes the finances less difficult because you then have a little bit of a safety net to fall back on. I wanted to pitch, there's a new program from the NSF called US for Grad. Unfortunately, it's only available, I believe, to US citizens, but it's a fellowship that funds your PhD that is specifically for people who have been in industry and are looking to go back. So that can be a really great resource to check out. If you want to Google it, it's called US for Grad. Maybe throw NSF in there if you're thinking about going back to academia.
Sorry, I think there's someone on unmute mode. Anyways, okay. I'll bring up a different question for the academic job search. So I wanted to rather start with the basics to understand. Yes, you did mention in your talk in the beginning, like what motivated you to join the academia, even though you had a couple of years of industry experience, like you liked to teach. So right now, you're still collaborating a lot with the industry, and there you get to teach in the school. So what's the exact thing going on? Like what motivated you to bring a balance between the two?
Yeah, it's a great question. And I reflected on this a lot because there was, this clear deciding point as I reached the end of my PhD. And part of what helped me really make the decision is that I taught a class as an instructor of record while I was still a PhD student. So I taught our introductory data structures class over a summer. And that really solidified for me how much I feel like I'm sort of providing value to students as an instructor and a professor, and how I find it very, very motivating. And so I think I really just realized that that was something that I didn't want to give up. I will say, if people go back to industry after academia, you still get to do a lot of teaching in your day-to-day. You still, you might be writing documentation for developers, you might be working with interns and with new grads. So there's obviously still a lot you can do in terms of mentorship, but I really like the sort of teaching of foundations. And also this idea of, when I was an undergrad, I was initially very afraid of the systems class. And I found it really cool to like find my footing in systems and take distributed systems and programming languages and all of these classes that were very, very challenging. And I find it personally super motivating to try to be that person that can demystify the sort of system side of computer science for a new generation of students. That's a little dreamy, but that is one of the things that definitely motivated me. And yeah, I think another distinction though is that because I care so much about teaching, I made the decision to not apply for lots of universities that were more like the universities I had attended. So universities like Brown and Cornell produce a lot of PhD graduates. They're what we oftentimes call R1 or Research 1 universities. That's just defined by the amount of research that they do. And R1 universities tend to be like the goal that's set up after a PhD is like, you go to an R1 university and then you have your own lab of PhD students and you sort of continue on in that tradition. And the reason I didn't want to do that, at least right now, is that I find teaching so motivating that I wanted it to really be a core part of my job that is part of my evaluation. So I'm in a tenure track role, meaning I do this job for some period of time and then they decide whether or not to give me a tenure appointment. And at schools that are more undergrad focused, like Wellesley, that is really almost a 50-50 balance between research and teaching. Whereas at a lot of universities that are this like R1 status, it's going to be more heavily leaning towards research and towards graduate classes. So that was sort of my decision. And I think part of why I bring this up is just that I think a lot of PhD students aren't exposed to these opportunities at non-R1 institutions. And so it can be a really useful thing to just think about if you're a PhD student who enjoys teaching. So things to Google for that search is either looking for specifically, I'm going to a liberal arts college. So that's one thing you can look at is like liberal arts colleges. And then the other term you can Google is PUI, or primarily undergraduate institution, which is a broader class than just liberal arts colleges. It includes like a whole range of schools, like a lot of state schools don't have PhD programs and are considered primarily undergrad institutions. So yeah, there's a lot of jobs that exist in academia that aren't as heavily research focused, but you still can have a balance of research.
Mm-hmm. Yeah, that's great to know. I mean, I wanted to particularly, bring up this question of different tracks, which exist in different kinds of schools and universities in general. So is it easy to switch between these tracks? Like, let's say, you started working here and maybe 5 years down the line or 3 years down the line, you feel like, I'm going to set up my own lab now and I'm ready to go and choose a school, which is also dedicated more towards the grad, curriculum. So would you be able to switch careers?
That's a really great question. In some ways, I don't have a great answer because I'm just, starting this job now. I started July 1st, and so I don't feel like I have the best answer there. I will say that in making this decision, I reached out to probably dozens of people across these different jobs, and some of them have switched back and forth. So there are definitely people who have made that transition kind of in both directions between different types of universities. There's also, of course, people sometimes bounce back and forth between academia and industry. I think one thing that's a little true is if you take a permanent industry position after a PhD, going from that to the R1 route specifically, like that intersection seems sometimes hard. Postdocs are a little different. And I also, again, like I haven't done it, so I'm definitely not a definitive voice on that. But sometimes there can be challenges with switching back and forth at sort of the very, very research heavy end, but people do it all the time. So I definitely think it is feasible. It looks like there's also a question in the chat, so maybe I'll answer that next. So the question is, what did you find among the most interesting or unexpected differences between the approach to compilers research in academia and in industry? And your experience, what would be the most valuable industry compilers teams can learn from academia? It's a great question. I think one of the big differences is just in terms of what people consider valuable. A slight challenge with academia sometimes is that there is this idea that in order to get publications, which is unfortunately part of how the academic machine works, there's this idea that things need to be novel. And so I would say that academia cares more about the novelty of a system, even if production sort of industry teams care about how well does it work in practice. And these can actually be at odds, because sometimes what works best in practice is to not reinvent the wheel, to take existing knowledge and apply it and tackle the new challenges in your particular domain, but to very much not reinvent the wheel. Whereas academia is okay with that in some sense, but you also have to sort of sell your work in a way that makes it clear that there is a new contribution to how we actually approach problems as well. So balancing that line has been a little bit hard for me of trying to do work that is very practical and definitely acknowledging that I'm like standing on the shoulders of giants for all of this work. None of these ideas are brand new, but still highlighting what the key new contributions are in order to also make it amenable for publication. In terms of what can compilers teams learn from academia, I think there's a ton of answers there. I think some of the answers that I tried to highlight in this talk are that more declarative approaches, even if they require more upfront costs, are really valuable in terms of being able to do higher level reasoning. So what I mean by more declarative is that if you're thinking of like your first implementation of a compiler, just having like a bunch of direct compiler implementation code that does like ad hoc matching is going to be like the fastest thing to implement. But if you take the time to design an interface where you can have something that's more like a domain-specific language or more structured in how you modify the input programs, that's going to make it easier down the line to do more higher level types of verification. I think also like Cranelift, I want to be clear, does a ton of fuzzing as well. So I didn't talk about fuzzing much in this talk, but fuzzing is, again, a kind of point in between testing and formal methods where you are testing concrete inputs, but you're automatically generating tons and tons of them. And so I think the other thing that, I think industrial compiler teams could take away is that there is this really broad spectrum in academia of what we mean by validation or verification. And you can pick points along that spectrum that aren't spending like many, many years doing something, but are sort of pay as you go, where you put in effort and you get out results, even if you don't have an entire formal mechanized semantics.
Yeah, and I think it is also a great way in general right now with a lot of academia and industry collaborations going on. Not just today, they have been going on for several years, right? Decades. So whenever that happens, I think the academic people can bring those in-depth insights and so on and apply it in real world. So, both sides, get to learn so much from each other in that way, So I feel that that's a positive way to kind of continue research and put it in practice.
So going back to some of the technical aspects, right? Could you kind of go under the hood of these formal methods, the umbrella, called formal methods, and talk, in brief about how exactly this kind of testing is achieved?
Yeah, that is a super great question. And if I'd had more time, I definitely could have gotten more into it. So the high level idea is a little different depending on which technique you're talking about. But let me actually go back to this slide, might make it a little easier, all these crazy math terms. So when you use one of these things called an SMT solver, what SMT stands for is satisfiability modulo theories. And satisfiability is a really kind of core question in computer science. You might have seen it if you took a class on like theory of computation or discrete math, where the question is, if you're thinking of pure Boolean satisfiability, if you have a bunch of clauses of like ands and ors on Boolean, so if you have like A and B or C and D and a bunch of things like that, satisfiability is the question for some assignment of true and false to A, B, C, D, is the entire formula true? And this is super important on lots of different questions. And it turns out it's a very, very hard problem. It is an NP-complete problem, meaning we do not have extremely efficient solutions to be able to solve these problems in general. So SAT solvers are implementations of answering that decidability or that question. And to be clear, when I said the problem is very hard, we don't have efficient solutions, but pure Boolean satisfiability is what's called decidable, meaning there's always an answer, either yes or no. Either there's some possible assignment or there's no possible assignment. And you can maybe convince yourself that there is this answer because you could say you can just like manually try all possible options and then find one or not find one. So SAT solvers are the implemented equivalent of that brute force solution with a bunch of tricks up their sleeves that sometimes make things faster in good cases. So what a SAT solver does, just a pure Boolean SAT solver, is it's going to try using sort of recursive solution to find you assignments of values that either sort of are a witness to say, here are the assignment of values, the formula is true, or to tell you, no, there's no possible assignment of values. And it can do reasoning that's a little smarter than just try all possible values. You can sort of do things like if you know one constant is by itself, maybe that has to be true or has to be false. So what SMT solvers do, so that was all Boolean satisfiability, also known as just SAT solving. What SMT solvers, the MT is for modulo theories, which says, hey, Booleans are cool, but we have other things in computer science than Booleans. We have things like integers, like we have things like real numbers, which are sort of real mathematical, what am I trying to say? I don't remember if they are rational or irrational. Anyway, like basically mathematical models of floating points. We have floating points themselves. We have bit vectors, as in literal zeros and ones in a vector. And so SMT solvers add on to Boolean satisfiability the ability to write formulas over these theories. So instead of just saying A and B are Booleans, true or false, you could say A is some integer, B is a bit vector with 5 zeros or ones, etc. And then the SMT solver is again going to do this job of trying to either find you a model that the entire formula is satisfiable, or tell you that there is no satisfying solution, oftentimes using tricks like, if you ask a SAT solver, X is less than 0 and X is greater than 0, find me an X. The SMT solver is not going to just try all possible values of X. It's going to use properties about integers to tell you that that's impossible. So they're doing some sort of combination of this brute force reasoning and applying identities and axioms about values in order to give you a solution. So all of that is kind of under the hood of SMT solvers. They, like, according to theoretical computer science, these are very hard problems that cannot be efficiently solved. But in practical, real world use cases, there are a lot of problems that can be solved by these within seconds. And so there's sort of over the past 10 years, there's been a growing use of things like SMT solvers. The other side of formal methods that I called foundational formal methods, I'm honestly less familiar with, but what those tools use is the mathematical relationship between proofs and programs and dependently typed programs in order to sort of deductively build up program correctness. But I do not have as good of an answer there because it's less my area of research. Sorry, that was a long answer.
Thanks, that helped.
So a follow-up question from what we were discussing about the different tracks and the career paths that you have chosen, where there's a balance between teaching and research. I wondered, like, how is the funding and grants situation in Wellesley College in particular? Like, does your college allocate a chunk of fund towards undergrad research positions? When students get to work with you, are they paid by the college themselves, or do you have to take care of arranging, funding for all of the students that work with you?
Yeah, that's a really great question. And just to give an overview, if people aren't as familiar with academia, the way academia works is that professors are paid a salary to teach, even if they're at a research university. You're paid for 9 months of the year to teach, but you are also expected to do research. And in order to do research, you need to pay students typically, and that money has to come from somewhere, and it's usually not just the university. So there's all of these mechanisms around how PhD students are funded, which is why when I mention that fellowship, I want to be very clear, even if you don't have a fellowship, you should never pay for a PhD program in computer science in the United States, or really most of the rest of the world. So the PhD programs are funded, but if you are not on a fellowship, they're funded by your advisor's grants. So your advisor has to apply to the government or to industry and say, please give me money to do this project. They say yes, and then that money through the university gets filtered to you. And the same is true for undergrads, that undergrads sometimes work on research as part of courses or as honors theses, but a lot of times also they're paid research assistants. And schools like Wellesley do provide you with what's called startup funding, meaning that when you start as a professor, you get an initial pool of money with which to pay students. So my particular college has some funding that's just always there for students, regardless of grants. So you can always have sort of a certain number of summer students. And then additionally, I have some startup funding, which covers not just students, but also covers my equipment. So I like to work with big, powerful servers. So I'm going to buy myself one of those soon. And things like if I want AWS credits, that can come out of that pool of money. That's something that's negotiated as you're navigating the job market. This does vary a lot based on the position. So some primarily undergraduate institutions have sort of less of an expectation that you do as expensive of research, in which case you might have a smaller amount of funding that maybe funds a few students a semester and less funding for equipment, or you are expected to sort of collaborate with other groups at universities that have more expensive equipment, for example. Yeah, and then I also, as now a tenure track professor at school, I'm also applying for grants to continue to fund my research in collaboration with folks at universities.
Mm-hmm. Yeah, that's cool. And I would assume all those kind of tips and learnings about, how much funding should be enough to, kind of accommodate n number of students and so on, that you can gather from your advisor or other, academic professors around you in your network.
Yeah. And there are also a good number of resources online. Computer scientists tend to be good about blogging and stuff. I have been planning on putting my experience on a blog. I haven't done it yet, but there are lots of posts around the job market and navigating these differences. And I think just in general, even just looking at job postings, there are also lots of jobs that don't have as much of an expectation of research. So for example, you could be a professor at a community college where maybe you do a bit of research in the summer, but the semester you might be teaching 3 or 4 classes and be very focused on teaching during the semester. So if you're someone who really, really likes teaching and are okay having research be a smaller portion of your time, then there are also jobs that might suit you kind of different places along the spectrum.
Mm-hmm. And about the course preparation, and also about the job requirement. So first about the job requirement, when you're choosing colleges, right, like where you have to teach and do research, in a balanced way or in either way, right? More research and lesser teaching. So what are the requirements exactly? Like, do they kind of look for the number of papers or journal publications or the courses that you have taught as a TA or, otherwise? So what exactly is kind of, looked at?
Yeah, it's a great question. So for most tenure track roles in computer science, you do need a PhD. This is not true for all. So especially for institutions that don't have graduate students, for places like community colleges, some state schools, you can oftentimes teach with a master's. So you typically need at least one degree above the highest degree that the school offers. But if you have a master's degree, you can teach there. Lots of jobs, though, do require a PhD in computer science. And they want to see evidence of substantial research. So no one is going to directly tell you, like, here's the number of papers that you need. And I would say even less so than my impression of the job market. They're much more flexible on that. That doesn't mean, it kind of depends on the particular school too, but you need to have a very solid trajectory of research and of publications, even though no one's going to precisely tell you the number. And then I think to be sort of the most prepared for these schools and colleges that really try to emphasize teaching, having taught before as instructor of record or co-instructor of record is super helpful. I wouldn't say it's a firm requirement, is my impression. If you have a lot of TA experience at the graduate level or have taught sections, that might be good preparation as well. But I think I just recommend that students who are interested in this path do teach, because it's very, very different from TAing. And I don't think you can, it's hard to commit to what could potentially be a lifetime appointment if you get tenure, if you haven't done the job. There's a little silliness with academia that a PhD doesn't really prepare you for the job of being faculty. And so you kind of have to take steps yourself to try to understand if it's the right role.
Yeah. And any tips for, people who, kind of figure it out later to enter into this academic world, but they didn't get a chance to, explore much of a teaching and so on?
Yeah, that's a really good question. I think there are opportunities to teach in shorter term roles. So a lot of times, because it's very hard for these schools to hire sometimes, because in general, it's just there's a big market for CS PhDs compared to PhDs in other fields. And so there's more job competition for universities and colleges. So a lot of times they will hire either visiting professors or adjunct professors. So what I've seen people do sometimes is in the city where they live, they look at local colleges, all sorts of local colleges, and apply to, especially if you have a PhD or a master's degree, you can apply to teach an individual class at a given school. That's, I think, one path to figure this out. Sometimes those are slightly longer term, so they are year-long or 2-year-long visiting professorships at a college where you would go and actually live there, move somewhere else, and teach for a year or two. Yeah.
Very cool. Yeah. And how did you shortlist the colleges? It's a hard problem, I believe. I think the most harder thing is, how do you even stay, informed and very updated about who's looking for new faculty, besides, we have our network to talk to, but in general, what did you do to shortlist the colleges?
Yeah, it's a great question. I think we are very fortunate in computer science that there are more positions than other fields. So in our field, lots and lots of colleges and universities hire every year, which is awesome. And if you talk to colleagues in math, that is not as true. And so, yeah, I think just starting with a really broad sense of where in the country do you want to live, what type of place do you want to be, can be helpful. I will say the smaller the college, the less likely they are to hire every year. So some schools I was interested in just weren't hiring the year I was on the job market, and you just kind of have to accept that. But I was fortunate, or lots of candidates have been fortunate, that for the past few years, Evan Peck, who is a professor at Bucknell, which is another small liberal arts college, actually curated a list or maintained a list of primarily undergrad institutions hiring in computer science. And so that was sort of my starting point, was to, once that list started rolling in the fall, I think it's usually around August, September, that jobs start being posted. You can also look at last year's or prior year's lists to see what jobs are being posted. And what really helped me decide is thinking a lot, again, about this combination of location and wanting support for research and teaching. So that was my big thing. I wanted to be sort of closer to a city, which is sometimes a challenge because a lot of liberal arts colleges are more rural. And so that can be a little tough to navigate. But yeah, for me, it was a balance of location being really important to me, being able to build a community, and then having a school that really matched my values in terms of having close to equal focus of research and teaching.
I see. Thank you for sharing that. And very excited to know, like, what course are you going to teach this fall?
Yes, this fall I'm teaching 2 sections of Foundations of Computer Systems. So that's the sort of first time students learn programming in C and deal with things like pointers for the first time, understand digital logic and sort of the lower level components of hardware. And I'm really excited to be teaching that in the fall.
Yeah. And do you also get a flexibility to kind of, design your own courses, just like, professors who come for the graduate track, they kind of start introducing those seminars and, sometimes very specific courses just around their own research. Do you have that kind of flexibility here at some point of time?
Yeah, absolutely. It's definitely college dependent and department dependent. Depends on what faculty are around at a given time, who's on sabbatical, all of those things. But I do expect to teach a course that is new to WICT in the next couple of years. So I'm really excited to teach a course that's this idea of sort of lightweight formal methods, could call it logic for systems, like the course I took at Brown. Names are hard, but yeah, I'm excited to teach a course closer to my research area. I think compared to a graduate institution, it might not be as hyper focused on exactly what I do, but more like a more general introduction to my field. Wellesley also has not had a compilers course in a little while, has not had an operating systems course in a while. So there are sort of a range of courses at different levels of the undergraduate curriculum that I'm excited to teach at some point.
Yeah, there's a lot of opportunity, I would say, for students to now learn new subjects, new topics, which are so exciting nowadays. So that's great. And overall timeline, like how early one has to get started to start preparing for the job applications.
Yeah, so I finished my PhD in 5 years total. So basically the end of my 4th year was when I was really seriously thinking about what I wanted to do after my PhD. So the end of my 4th year is when I taught for the first time, and when I also began thinking about if I was going on the academic job market, who did I want to write me letters of recommendation? So when you apply to a faculty position, that's one of the most important components, is you have anywhere from 3 to 5 letters from people with PhDs typically about your application. So you also have to have a research statement, a teaching statement, in many cases a diversity statement, and then you prepare to give a job talk. So actually some sections of today's talk were from my job talk that I gave when I was on the market. Schools that are more teaching focused also have you prepare a teaching demo. And I will say this is one of the most challenging parts of this market, because if you're getting advice from people who have not done a teaching focused market, this is also shocking to them, because it means every single interview you do, or almost every interview, you have to prepare a different teaching demo in addition to your job talk. So that can be very hard, and means that in terms of timeline, starting in the summer, at least with some of the basics, is good. These jobs get posted oftentimes earlier than the corresponding R1 jobs. So jobs get posted in late August, September, October. I think the first deadlines for me were in early October, which is quite early. So early October of my 5th year, I was submitting applications, conducted interviews, like phone interviews, October, November. So jobs typically have like a phone or Zoom interview first, and then in-person interviews, November, December. And I actually, decided my position by the end of December, which is much earlier. If people are familiar with the R1 job market, that happens much more in the spring. So that's more spans like submit applications in December, start interviewing in January, and spans all the way to like May. So it is an earlier process for liberal arts colleges, at least.
Yeah, very cool. And I think, it's a very lengthy process. So congratulations to you on accomplishing such a heavy weighted, process. And you landed up in a great college. And I'm sure you'll do wonders in the rest of your career. I think one question I want to open up so it could help a broader audience, not just who are attending here, but for people who might be watching this video later on YouTube. I wondered, would you be open to more collaborations with people who are in the industry, even those people who don't know yet or have not worked before on, let's say, the formal methods and so on, but they have worked on compilers or either way, right? So how they can get in touch with you, and what kind of collaborations are you seeking in general from both students in academia to industry people, who have some experience right now?
Yeah, absolutely. I am very open to collaborations. People can definitely email me about collaborations, and just if they have questions about the talk or about any of the things I talked about today. You can find my email by Googling me for my Cornell email. My WICT email, I think, is not on the internet yet, but I will put it on the internet soon. And in terms of, what I'm open to, I think I'm really interested in production compilers or compiler projects that are sort of actually being used in practice and are open to integrating formal verification, especially in things like continuous integration. So the ability to sort of get formal verification, at least the lightweight version, to be more similar to things like unit tests is a direction I'm very excited about. And yes, same sort of open to students and folks in industry with those general interests. I also, once I, I have not yet moved to Wellesley, even though I have started my job. I am moving to Wellesley in 2 weeks. And once I do that, I'm also going to be looking for Wellesley undergraduates to do research with me as well. So I will have more students that I will be advising on projects, and really excited to work on projects that are sort of motivated by external use cases as well, even ones that I haven't thought of yet.
Yeah, absolutely. Thank you for sharing. And it was really wonderful, listening to your talk, learning a lot of great insights, and also through this EMA, I think a lot of us are going to learn so much. I have personally learned a lot of things, and I think it's very motivating as well to look up to someone, who just, finished their grad school and already started to think about this academic job careers and forming great industry collaborations already, they're running. So this is great. I wish you all the success. If there are any more questions from anybody, please feel free to ask. Otherwise, we are ready to wrap up.
Well, I will say also the paper describing the work in this particular project is a preprint currently, so it's still a draft preprint. You can find that on my website. And if you have questions about that paper, that this is the one paper that I can still change because it is not it's not formally published yet. So definitely reach out to me if you have comments on the paper as well.
Yes, it's on my list too. I remember I have to read. I was, reading it today, but I have to finish it.
I had one question. So with all this buzz around AI, right? So how is the undergraduate curriculum changing, and is it happening at the expense of some of the more traditional and foundational courses?
Yeah, that's a really great question of how is AI changing undergraduate education. And I think, again, because I'm starting as a professor like this coming semester, I don't know that I have as much insight as someone who's been teaching for the past 2 years continuously, who has sort of seen things like ChatGPT rise to the forefront more than I experienced. But I think the philosophy I am trying to take is that it's always been the case that students get out of a course what they put in. So I try to not see my students in as adversarial of a light, where I want to try to explain to students why AI-based tools can be useful in some contexts, but don't replace the foundational low-level knowledge of the systems themselves. And I have an intuition, I haven't played with that ton myself, that these large language models are going to do a lot worse of a job programming low-level pointer manipulating C code than they might do writing Python code. I don't know that that's true for sure. We'll see. I think there's a lot we still have to learn as educators and as computer scientists about how those things interact. I don't think in my plans for this year, it will incredibly substantially change my curriculum. I plan on having discussions with my students on sort of acceptable uses of these tools and how I think you can best use them without harming your learning. But I think this will become a thing over the first several years of my career as a professor that I'll have to think about more and more.
Right. So that makes sense. So I guess the other question was that about the courses itself, right? Do you think that operating systems might become an optional course while AI, a deep learning or a machine learning course be added as something that as another track or as another foundational course that you can take for the degree requirement, because of its prevalence?
Yeah, that's a great question. I think schools will probably vary in how quickly they adjust. I don't know that immediately, like this year, schools are going to be changing that rapidly. They tend to have a slightly slower clip of changing courses. And I will say at liberal arts college, something like operating systems is not actually a required class at Wellesley. So computer science programs even vary for what they consider required. My personal take is that I don't think we should stop requiring some of these foundational courses. Like I don't want to stop requiring data structures or foundations, introductory computer systems, for the same reason why I still think we should teach calculus, even though we've had Mathematica and lots of programs that can do calculus for a while. So I think some of the core curriculum of computer science should be core, even as large language models impact how often people need to use those specific skills. But I'm also just a little bit skeptical about how quickly they will actually revolutionize things, given that I think the big weakness of large language model driven code is correctness, and correctness matters a lot to the type of programming that I do. And so I am a little bit skeptical of how quickly it will be able to sort of like change the daily lives of compiler engineers, for example. So yeah, I don't, again, because I'm very new faculty, I don't know that I have as nuance of an answer as someone who might be a department chair who is really thinking about how they're shaping their curriculum, but I do think it's a really interesting thing to think about.
Cool, thanks.
I think we can wrap up the session. Thank you everyone for joining. And thank you, Alexa, again, for sharing all the insights today. We look forward to having you again sometime in the future.
Thank you.
Yeah.